Have you ever wondered why fewer people have visited the bottom of the Mariana Trench, the deepest point in the ocean, than have traveled into space? While more than 600 humans have orbited Earth, only a handful have descended nearly 11,000 meters, 36,000 feet, into the depths of the ocean. It seems contradictory. After all, space is often considered the final frontier, while the ocean is right here, on our own planet. But the truth is that the deep ocean hides a brutal challenge that is often underestimated: pressure. While spacecraft must survive the vacuum of space, submarines face forces powerful enough to crush steel as if it were paper. Today, we're going to dive into this fascinating question and discover why mastering the depths of the ocean can be even more difficult than reaching Earth's orbit. What makes deep-sea pressure so terrifying? To understand the difference, we need to compare the environments. In space, a spacecraft maintains an internal pressure of about 1 atmosphere, similar to conditions on Earth's surface, while the vacuum outside exerts virtually zero pressure. In other words, the spacecraft's structure only needs to contain the air pressure pushing outward from the inside. Think of it like an inflated balloon. At the bottom of the ocean, however, the situation is completely reversed. Every 10 meters, 33 feet, of water depth adds approximately 1 atmosphere of pressure. At the Mariana Trench, nearly 11 kilometers deep, the pressure exceeds 1,100 atmospheres. To withstand this incredible force, a submarine must be built like an armored fortress, while a spacecraft is more like a sealed container designed to keep air inside. How do submarines avoid being crushed? To survive extreme compression, deep-sea submersibles rely on 2 key factors: geometry and materials. The spherical shape is the strongest possible design for distributing external pressure evenly across the hull. That's why most deep-diving vehicles use spherical crew compartments. The second factor is material strength. The limiting factor submersible, which reached the Mariana Trench, uses a titanium sphere approximately 90 millimeters, 3.5 inches, thick to protect only 2 people. Even with this advanced engineering, a single manufacturing defect, improperly installed bolt, or imperfect weld could result in catastrophic implosion. By comparison, spacecraft such as SpaceX's Crew Dragon primarily use lightweight aluminum alloys and carbon fiber composites. Their walls are much thinner because they are designed to hold pressure inside rather than resist enormous pressure from outside. Understanding the mathematics of pressure. The pressure exerted by water increases with depth according to the hydrostatic pressure equation. P equals rho GH, where rho is the density of water. Approximately 1,000 kg/m superscript 3g is gravitational acceleration, approximately 9.81 m/s superscript 2h is depth. At a depth of 11,000 meters, the pressure reaches approximately 107,800,000 pascals, or 107.8 megapascals MPa. That's enough pressure to pulverize solid materials and destroy most structures instantly. For comparison, the pressure difference experienced by a spacecraft in orbit is roughly 0.1 MPa. This means deep-sea pressure can be hundreds of times greater than the pressure loads typically encountered by spacecraft. Why is a leak more dangerous underwater? If a spacecraft develops a leak, the air gradually escapes into space. It's obviously dangerous, but the process can be relatively slow depending on the size of the breach. In the deep ocean, however, water is nearly incompressible. Any crack or opening allows water to rush inward at incredible speed, causing an implosion. An implosion occurs when external pressure crushes a structure inward almost instantaneously. One tragic example was the nuclear submarine USS Thresher, which was lost in 1963 at a depth of approximately 2,400 meters. Another recent example was the Titan submersible, which imploded in 2023 during a dive to the wreck of the Titanic at a depth of around 3,350 meters. In both cases, the immense water pressure caused catastrophic structural failure in fractions of a second. Why don't spacecraft use titanium? If titanium is so strong, why not use it for spacecraft? The answer is simple: weight. In spaceflight, every kilogram matters. Launching mass into orbit is extremely expensive, So engineers prioritize lightweight materials such as aluminum alloys, carbon composites, and advanced ceramics. Deep-sea submarines, on the other hand, are willing to sacrifice weight for strength because surviving the crushing forces of the ocean is the primary concern. The real challenge of ocean exploration. Although space appears more distant and mysterious, the deep ocean presents unique engineering challenges that can be even more demanding. Spacecraft must keep pressure inside. Submarines must keep crushing pressure outside. The difference may sound subtle, but from an engineering perspective, it changes everything. The ocean floor remains one of the least explored places on Earth, not because it is far away, but because the forces acting there are among the most extreme environments humans have ever attempted to survive. So what do you think? Would you rather travel into space or descend to the bottom of the Mariana Trench inside a submarine? Let us know in the comments below. Don't forget to like, subscribe, and turn on notifications for more engineering and science content. Rocket Waterwave.